All right, well, welcome to Chapter 2. In this chapter, we're basically going to be taking a lot of what we did last year in Advanced Algebra and putting it all into one chapter. So last year, we really focused on a lot of different functions throughout the year. And so that's what this chapter is all about. This unit is all about functions. And so to start out, you might want to pause this video and write down these terms and their definitions. If you don't have my notes printed, some of these you may not need necessarily, but the ones that I just want to highlight that are the most important is you want to make sure you understand what's the difference between an independent variable and a dependent variable, and what's the difference between a domain and a range. And so just to go through these, so a relation is just any set of ordered pairs. So if I just wrote down a whole bunch of coordinates, that's a relation. Now, to skip down, I'm going to skip past the independent and dependent, but to skip down to what a function is, so a function is a special type of relation where each x is paired with one y. Now in Advanced Algebra last year, we had this analogy of a snack machine, and we talked about that if you had a snack machine that was a well-operating snack machine, if you went up to it and typed in like D3 and got M&Ms, if you type in D3 again, you should still get M&Ms. You shouldn't get two different things. And so each x, or every input, you'll get exactly one output. So for every x, you'll get one y. That's what a definition of a function is. Now, it would not be a good function or a snack machine if I walked up to that machine and I typed in D3 and got M&Ms, and the person after me typed in D3 expecting to get M&Ms, but then got a Snickers bar. Although I wouldn't complain about that, that would not be an example of a function, because here you typed in, you had one input, but you had two different outputs. So that's another way to look at it. That is how we can see if it's not a function. So we have these two variables called independent variables and dependent variables. So an independent variable is what we would call that input. It's what we put in for x. And what you get as your answer, that's the output, and we call that the dependent variable. Now we have a special thing too, also called the domain and range. Now we did a lot with the domain and range last year, so this should be review. So the domain is all of the x values in a function. So all of the possible x values that we could put into a function would be your domain. And the range would be all of the y values, all of the possible outputs of the y values that's part of the function. An easy way to keep these straight, so the domain is your x's, your range is your y's. And so if you think of D comes before R in the alphabet, X comes before Y in the alphabet. So since the D comes first, then it's paired up with the X. So the domain is the X values. Since the range comes second in the alphabet, then it's paired up with Y, because that comes second in the alphabet. So you should have gotten those copied down, but those are going to be some terms that we're just going to be referencing here. Now sometimes we're going to refer to, or we'll have a sentence, or we'll be referring to the different variables, and we'll say the dependent variable is always a function of the independent variable. So that is, when describing a function, that's the phrase we're going to use. So let's look at this example. Here it says, a bakery charges $2 per muffin. Customers get a $2 discount for every 6 muffins purchased. So we want to take from that and identify what the independent and dependent variables are going to be of that function. So the way that you can think of it is, so we got a couple of things going on there. So a bakery charges $2 per muffin, and they get a discount of $2 for every 6 muffins they purchase. So we want to figure out what are our variables. So let's start with the independent variable. So the independent variable is basically it's what is going to happen no matter what. Okay, so sometimes you just have to put yourself in the shoes of the story problem. So you're going to walk into this bakery, and what are you going to do? You're going to order some muffins. And so you get to decide how many muffins you get. You could get 1 muffin, you could get 12 muffins. You can get as many muffins as you want. So the independent variable is going to be the number of muffins, because that does not depend on anything. And now we want to figure out, well, what's the dependent variable? So the dependent variable depends on our independent variable. So in this situation, what's going to depend on the number of muffins? Well, that's going to be what we spent. So the total cost will end up being the dependent variable. So now we got to figure out, so now we have our two variables there. So we have our independent variable and our dependent variable. So we got to figure out which of these statements is true. The cost, C, is a function of the number of muffins, or would we say the number of muffins is a function of the cost? And so what we would want to do is we want to phrase, again, we're going to phrase it. If we look back up above there, we always phrase it in this form. We always say the dependent variable is a function of the independent variable. Well, the dependent variable here is the cost, and the independent variable is the number of muffins. So we would phrase this by saying the cost is a function of the number of muffins. So this would be the proper way to refer to it as. All right, so now let's identify what the domain and range is of the function. So here we're dealing with a story problem. And so sometimes these can be a little tricky. So you got to think, so the domain is, remember, our values for x, which in this case is going to be, so our independent variable is the number of muffins. So the domain is going to be the number of muffins that we buy. Now you got to think of what kind of numbers could that be? So what's the least number of muffins that you could buy when you walk into the bakery? And if you said 1, you're close, but actually you're not being forced to buy anything when you go into the bakery. So the smallest number of, or the least number of muffins you could buy is 0. Now what's the most number of muffins you can buy? Are you limited by that? Well, really, your only limit is the number of muffins that the bakery has. And we don't know what that limit is. So what we're going to say is we're going to say the domain for this would be the number of muffins are going to be greater than or equal to 0. Or another way to phrase this would be, you could say the non-negative integers. Now, why did I say that? Well, non-negative integers, that's just referring to obviously positive numbers. Now you might say, well, why didn't we just say positive numbers? Well, think about 0. Remember, 0 is neither positive nor negative. And so if we said non-negative integers, that's going to eliminate any negative numbers, leaving us with the only option of having 0 or more. And so those are just a couple of ways that we could refer to the domain. Now let's think about the range. So what's the least amount of money that we could spend? Well, hopefully after that, the domain question, hopefully you're thinking, well, I don't have to spend anything. So you're right. The least amount of money that we could spend would be $0. And so the cost, or the range, you could say this very similar to what we did in the previous one. We could say the cost is going to be greater than or equal to 0. Or just like before, you could say non-negative integers. Okay, so either of those would be correct. Now, we need to be familiar with another type of way to refer to domain and range. Now again, we did this a lot last year in advanced algebra, but if you forgot, this type of notation is what we call interval notation. And this is really important. This is something that you're going to use regularly throughout this semester and throughout this year, and even going on into your future math classes. You need to be familiar with interval notation. So we use, remember, a mixture, a combination of brackets and parentheses. So we use a bracket anytime an endpoint or a value is included. And we use a parentheses when an endpoint is not included. So let's look at some graphs so we can be familiar with what we would use as far as brackets or parentheses. So here we have this graph. So this is a graph of this equation, y equals 2 to the x power minus 4. And so it says here we want to find the domain and range of the function. Okay, so let's start with the domain. Remember, the domain is the set of all the x values that we're including on the graph. And so the x value, so if you think about, if you trace the x-axis, and if I trace this graph, if we start, okay, remember when we list something in interval notation, we always start with the smallest number. So as I look at this graph, there is no smallest number along the x-axis, because I could keep going along the x-axis through infinity in the negative direction. Or another way to look at it, if you had me last year, maybe your advanced algebra teacher told you this last year, if we were to squish this graph on the x-axis, if I were to squish that down, we'd have an arrow going in both directions. And so the way we're going to describe this is we're going to say that it comes from negative infinity. So there is no smallest value along the x-axis. It just goes to negative infinity. Now, anytime we refer to infinity, we're going to use parentheses. And as we travel along this x-axis to the right, we just see that we can continue to use any numbers in the positive direction as well. So we would have, the domain would go from negative infinity to infinity. Now, if that confuses you, we could also look at the equation. We could look at the values for x. And we could ask ourselves, is there anything that I can't use as an exponent? So that's oftentimes what I'll do. I'll look at the value for x, and is there anything that I can't put in there for x? Well, I can put negative numbers in as exponents. I can put fractions. I can put decimals. I can put any number I want, even 0, I can put that in for x. So I have no limit there for what I can use as my values for x. So the domain then would be everything. So from negative infinity to positive infinity. Now our range, we do have a limit on our range as far as what values we could have. Because if you notice, our values here on the y-axis, if I were to squish this on the y-axis, we'd have an arrow going up, but would I have an arrow going down? And if you said that, well, we have an arrow over here, so if I squish it, we'd have an arrow going down. The problem is this arrow is being bent. Okay, we're going to learn about a term later on called an asymptote. You might remember that from Advanced Algebra 2. But that line is being bent right here where y is -4. So what that means is that this graph is not touching, it's bending as it gets closer and closer to -4. So there is never going to be any values down here below where y is -4. So what we're going to do is we're going to say that that graph starts at -4. Now, is it going to be exactly -4? And the answer for that is no. It will never be exactly -4. It's getting closer and closer to -4, but it's never going to become exactly -4. Now, you might be wondering, well, how would I know that? Well, if we look at the graph, there's nothing I could put in here, because remember, if this were 0, 0 minus 4 would be -4. So I can ask myself, is there anything I could put in there for x that would give me 0? And if you're thinking 2 to the 0 power is 0, well, no, remember 2 to the 0 power is actually 1. And so we can get really close to 0, but we'll never actually get to 0 there as far as putting numbers in. You'd have to put negative exponents in, and that just gets really ugly and funky. But just know you're never going to get 0 there. And so as a result, you'll never have 0 minus 4, so you'd never get -4 as an answer. But you can get really close to it. And then clearly you can see that this line, like I said, is going infinitely upwards. And so the graph would be going infinitely up. So since we're using infinity, the range we would say it goes from -4 to infinity. Now let's look at the next one. The next one, we're going to graph it on your calculator. So if you haven't gotten a TI Inspire calculator yet, remember you'll want to do that. Or for the time being, you can go to Desmos/calculator, or I'm sorry, Desmos.com/calculator is another resource where you can use a graphing calculator online. But remember, it's just best if you have a graphing calculator that you can use. All right. Whoops. So let's go. So if you're not familiar with the TI Inspire, let's review how to do this. So we're going to click on the home button there in the top right corner. And please don't use the scratch pad where it says graph, because if you go there, you can create a graph, but then every time you click on that, it's going to bring up that previous graph. And if you change any of the Windows settings, then you got to delete the previous graph, and it just gets to be a real mess. Or if you go down here and use the graph icon along the bottom, it'll always bring up a brand new graph, and we can always go back to any previous graph by clicking on the tabs up here. All right, so we want to graph that equation. So again, the equation was 3, and then use your parentheses, x minus 5. And then we're going to have the square button, which if you look over next to the 4 button, you're going to see a square button. So if you do that, and then -1, and hit enter. Okay, so we want to see what is the domain and range for this graph. Now, even though the window doesn't have arrows here on the ends, just know that it just keeps going up and up and up, meaning as we travel along the x-axis to the left or right, we're still going to get points in both directions. So in other words, if you look back at the equation, you could put anything you want in there for x. So the domain for this is going to be just like the domain we had before. The domain is going to go from -infinity to infinity. Now let's look at the range. Now from the graph, we might be able to tell what the range is. So it looks like the graph, the range, the lowest value is -1. If you're ever not sure, there's a couple things that we could do. We could go over here to the menu button, and what we could do is we could click the trace button, and then the very first option, graph trace. And if you toggle by using the left and right arrows, we want to go to the right here because I want to bring this down. So if we move I'm clicking on my right arrow, it shows us our minimum value there. So notice that's the lowest point. And it's showing us that our lowest point is where x is -1. Now there is a coordinate there. There is a coordinate where where y is -1. The coordinate 5, -1 is on that line. So when we go to when we go to write our range, the lowest point on that graph is at -1, and it is included. It is a coordinate that's a part of that graph. And so we would say it goes from -1 to infinity. Again, anytime we refer to infinity, we use parentheses. All right, so for this next piece here, again, you might want to pause the video so you can get a lot of this into your notes, because this is really important information here. packed into this 1 or 2 paragraphs. First off, if we ever want to tell if a graph is a function, we can use what's called the vertical line test. So if we draw a vertical line through the graph, and if it only passes through the graph in one spot, then it is a function. If it goes through 2 spots, like the one on the right there, it is not a function. So that's how you can tell whether a graph is a function or not. Then if we are working with the function, we have what's called function notation. So that's what's covered here in this paragraph. So function notation, remember, is written like f of x, and we use other letters. We can use g, we can use h. And then what's in parentheses, we call that the input. Okay, so if you have a number in parentheses or if you have x in parentheses, that's referring to your input. What you get is your answer, that's called your output. Or another way to look at that is that's the value. Okay, so all of that is very important to get in your notes. So pause the video and write that down if you haven't already done so. So we're going to do example 4a together, and then I'm going to have you guys do example 4b and try those on your own. This is just making sure you understand how to use function notation. So for this first one, for 4a, they have our input. They're telling us our input is going to be -3. So we're going to put -3 into the function and then simplify. Now you got to remember, anytime you square a number, especially if you're working with a negative, it's really important if you're using your calculator to use parentheses. So we would have -3 inside of parentheses being squared and subtract 4. Or this is easy enough to do in our head, because I think if I were to ask you if you squared a negative number, would your answer be positive or negative? I'm guessing 95% of you will get this right and say that, ooh, it would be a positive number. And so -3 squared would be a positive 9. And then 9 minus 4 would simply be 5. And so our answer for that would be 5. Now the next one, we don't know the input. Please do not make the mistake of putting 21 into the equation, because we don't know the input. That's what we're trying to find out. We're trying to figure out what would t be. We know the output. We know the answer is supposed to be 21. So we would have this as our equation. 21 equals t squared minus 4. Now if I solve this, I would solve for t squared by adding 4 to both sides. So I'd have 25 equals t squared, or t squared equals 25. Now you might think, well, the square root of 25 is 5, so our answer is 5. Well, remember, we could actually, if you square 5, yes, you do get 25. But is there another number that we could square that would also give us 25? If you're thinking that, well, -5 squared is 25, you are correct. So there's 2 possible answers for this one. We could have 5 or we could have -5 as your answer. And if you think, anytime that we solve an equation, so let's go back to this step. Anytime we solve an equation and there's a square involved, if you take the square root, oops, I didn't mean to zoom in here. If you were to take the square root of both sides to solve this, anytime you take the square root of both sides, that always means you're going to end up with 2 solutions, a positive and a negative. Okay, so that's always the case. Lastly, for letter C here, our input is another expression, meaning we're not going to get an actual answer for this. We're just going to plug 3p plus 1 in for t. So we would have 3p plus 1 being squared minus 4. Now for the time being, I'm just going to let you leave it like this. You do not have to worry about simplifying it. We can just leave this as your answer. If you did square it, if you did want to take this and get the answer, remember, you don't just square the 3 and square the 1. Remember last year in advanced algebra, we learned about this little box method. So you could do that and have 3p plus 1 here and 3p plus 1 here, because squaring something means you multiply it by itself. And you get 9p squared. 3p times 1 is 3p. 3p times this one is also 3p. And 1 times 1 is 1. So if we did want to simplify this, we'd end up with 9p squared. 3p plus 3p, if we add these two together, we would get 6p plus 1. But then we have that minus 4. So technically, the answer would be 9p squared plus 6p. And then 1 minus 4 is -3. So that would be the simplified version. But for the time being, I would accept this. But either one of those would be correct. All right. They won't always be that tricky. All right, I want you to try 4b on your own. So I want you guys to go ahead and pause the video and hit play when you're ready to check to see if you've done it correctly. All right, let's see how you did here. So for the first one, that's going to be the easiest one, part A. You would just put 5 into that expression. So we'd have 2 times 5 plus 8, all divided by 6. Or 2 times 5 is 10, plus 8 is 18. So our numerator would be 18. divide that by 6, and you get your answer there of 3. For letter B, so for that one, we know the answer is supposed to be 5. We're trying to figure out what the input would be to get an answer of 5. And so the way you could set that up is to say, well, 2x plus 8 divided by 6 is going to equal 5. Now, if you're wondering, well, how did he get rid of that fraction? Well, what we would do here is we would multiply both sides by 6. And so that would get rid of the fraction. So that would leave us with 2x plus 8 on the left. And 5 times 6 is 30. So don't forget about that piece. 5 times 6 is 30. So then I would just solve this two-step equation by subtracting 8 to get 22. Divide by 2, and you get your answer there of 11. And lastly, here we're just going to plug r plus 1 in as your input. So we'd have 2 times our input, so 2 times r plus 1, followed by the plus 8, all divided by 6. Now this one you can simplify because it's not that difficult. We would just distribute the 2 through in the parentheses there. So we'd have 2r plus 2 after doing that. And then we combine like terms in the numerator. 2 plus 8 is 10. Now you don't have to reduce this if you don't want to. You could just leave it as 2r plus 10 all over 6. And that would be your answer. So we covered a lot of information. We covered a lot of ground in this video. But I hope that after watching it, you'll be able to do well with the assignment that we'll do tomorrow in class. So just make sure that you come to class with any questions. And good luck on that.